Hi, I'm Professor Baldwin, and today I'm going to teach you about logarithmic functions. If x and b are positive real numbers and b doesn't equal 1, then y equals log with base b of x is called the logarithmic function base b. Notice that this logarithmic function with base b is equivalent to the exponential b to the power of y equals x. That's because the inverse of a logarithmic function is an exponential function. Now let's go over some terminology for this y equals log of base b. The value y is called the logarithm. Sometimes I refer to it as the result or the answer. B is your base, and x, what you're taking the log of, is your argument. Let's look at the first examples, and we're going to write each equation in exponential form. Remember that you get exponential form by taking the base, raising it to the power of that answer, or the logarithm, and it equals the argument. So 3 to the power of 2 equals 9. Let's do that again in example 2. You take the base, raise it to the power of the logarithm, and it equals your argument. So 10 to the power of negative 3 equals 1 over 1,000. In our next examples, we're going to go the opposite direction. So we're given exponentials, and we need to put them into logarithmic form. So to do that, your base here is the base of your log. So log of base 2. And the argument, what you're taking the log of, was your answer for your exponential form. And your exponent is equal to your answer, or the logarithm. How about example 4? The base of your exponent is the base of your log. Your answer for your exponent is your argument, and your exponent is your answer, or your logarithm. Now we can use the equivalence property of exponential expressions. So if b, x, and y are real numbers, and b is greater than 0 and also not equal to 1, then if you have b to the power of x and it's equal to that same base b to the power of y, then those exponents are also equal. So you can say that x equals y. Common logarithms. If you see the notation just log of x and there's no base number, it's implied that the base is 10. This is called a common log. If you see a log where it's written as ln, this is called a natural log. That's a base of e, that irrational number. In examples 5 and 6, we need to evaluate each expression. To do that, we're going to convert these into exponential form. So remember, we can set this equal to x, and the base of your log is the base of your exponent. And then your exponent is the answer for your log. And the argument of your log is the answer for your exponent. Now, to use that equivalence property of exponential expression, we can rewrite 125 as 5 to the power of 3. Since both sides have the same base, 5, we can set those exponents equal to each other. So we know that the solution to log of base 5 of 125 is equal to 3. Let's try that now with a natural log. The natural log of e to the power of 5. We're going to say it's equal to x so that we can find x. Remember, a natural log has a base of e. So this is e to the power of x equals our argument, e to the power of 5. The base is identical, e, which tells us that the exponents are identical. So the solution here for the natural log of e to the 5 is 5. This brings us to some properties of logarithms. On the left, you can see the property of the log, and on the right, you can see what that looks like in exponential form. The ones you're going to use the most often are probably the first and the second. If you take the log of 1, it equals 0, because b to the power of 0 always equals 1. The second one, notice that the base, b, is identical to that argument, b. When your argument and your base are the same, your result is 1. The base of your log is the same as the base of the exponential argument. And the result there is just the exponent on the exponential argument. And the last one, you have an exponent, which is a log. And because those bases are the same, we can set those up as it equals a log. Let's look at example 7 and 8. We're going to use those properties of logs to help us simplify these expressions. So notice in example 7, the base of our log is 13, and our argument is also 13. That is the second property here. So the answer is 1. In 8, we have an exponent. We have a to the power of log base a of 3. Since the base of the exponent is equal to the base of the log, this is equal to just that argument of 3. So our answer is our argument, this 3 on the inside. Now here's a quick overview of the graphs of exponential functions and the graphs of logarithmic functions, so you can see how they are inverses of each other. We're going to concentrate on the right here, these graphs of logarithmic functions. Notice that the domain of a logarithmic function is the same as the range of an exponential function, and it's from 0 to infinity. The range of our log function is all real numbers. It has a vertical asymptote. They pass through the point 1, 0, and our base needs to be greater than 1 for an increasing function, and it's between 0 and 1 for a decreasing function. Using this information and transformations, we're going to graph this function provided in question 9. Now, note that you could create a table of x values and find those corresponding y values and plot those points. But I think that transformations are very important. So first, let's identify what our mother function is. And here, that would be log base 3 of x. We also want to acknowledge what that base is. Base is equal to 3, which is greater than 1. Since it's greater than 1, we have a function that's increasing. So visually, we know our graph needs to look like this. Now, let's first start by plotting the points we know for our mother function. We know that it's going to pass through the point 1, 0. We also know from our basic properties of logs that if you take the log with a base 3 and your argument is the exact same value as your base, that is equal to 1. That would correspond to the point 3, 1. So we can plot that. To also help us graph, we want our vertical asymptote. Our vertical asymptote is x equals 0 for our basic log functions. Let's connect those dots. We know that our left side is going to approach that vertical asymptote, and we have our right-hand side. So we'll label this as log base 3 of x. We have 2 points that we can transform, and we also have our vertical asymptote. So let's look at what's happening to our mother function to end up with this new function. So first, we're looking for any horizontal transformations. This -1 inside tells us that we're going to go right 1 unit. Next, you're looking for those shrinks or stretches. Are you multiplying by anything? We're not, so there's no shrink or stretch. Third, remember, is to look for a reflection. Are you multiplying by a negative? We are not here, so there's no reflection. And then lastly, are your vertical shifts? Are we going up or down? And that's this -3 at the end. That tells us we need to go down 3 units. So our two transformations are right 1 unit and then down 3 units. So let's start with our first point here of 1, 0. We're going to go right 1 unit and then down 3. We have our second point of 3, 1. We'll go right 1 unit and down 3. Before we connect those dots and draw our curve, we also want to shift our vertical asymptote. And because it's vertical, we're looking for a shift left or right, and we need to move it right 1 unit. So our new vertical asymptote is going to be here, and that is going to be x equals 1. So we know that the left side of our transformed graph is going to approach that vertical asymptote, and then we can draw the right-hand side. Make sure you also label that function so your instructor can tell the difference between your mother or parent function and your transformed function. Thank you so much for watching. I hope you found this video helpful, and I hope you'll go check out some of my other math videos.